Let's talk about application of tangent line. Well, we can use the tangent line to approximate a function at a point and see how that works. Consider the function f that is differentiable at a point x equals a. Recall that the tangent line to the graph f at a is given by the equation y equals f of a plus f prime of a times x minus a. Find the equation with the tangent line to the graph of f of x equals x to the third at a equals 1. Then get the graph of f of x and its tangent line at a equals 1 on the same coordinate plane. So we know that f of x equals x to the third. Then f prime of x is equal to 3x squared. When x equals 1, then the equation of the tangent line, then y equals f of 1 plus f prime of 1 times x minus 1. So this is 1 plus 3 times x minus 1. That is 3x minus 3 plus 1. That is 3x minus 2. So let's get the graph of the function of f of x equals x to the third and the tangent line on the same coordinate plane. X to the third, so go to the point 0, 0, 0, 0, 1, 1, 2, 8, 2, negative 8. So so this is our x cubed. So f of x equals x cubed. And the equation of the tangent line is 3x minus 2. So the y-intercept is at negative 2. Slope is 3. And we'll connect this point to make the tangent line. So next, what I want you to do is to evaluate f of x. We want to compare the value of f of x and y at x approaches 1. Okay? We do that by evaluate the function at x go closer and closer to 1. I'll make the table value. Here's x. And we want x equal to, on the right side, 1.001, 1.01, 1.1, 1.01, 1.001 at 1. 0.999, 0.99, and 0.9. Okay, we evaluate the value for f of x for f of x and y of x, and y equal to 3x minus 2. I want you to go ahead and fill out this table. So as you can see that as x approaches 1, the value of f of x and y is almost the same. This meant that we can approximate the value of f of x by using the equation of the tangent line. So note that the value of f of x and y as x approaches 1 is almost the same. Well, this means we can estimate the value of f of x using the tangent line. Okay. So let's talk about linear approximation. If f is differentiable at x equals a, then the approximating function L of x equals f of a times f prime of a times x minus a. That is the equation of the tangent line at x equals a. And now we can see that we can clearly use it to estimate the value of the function at x approaches a. Let's take a look at the first example. We want to find the linear approximation of f of x equal to square root of x plus 3 at x equals 1. And then we use the approximation to estimate 3.1. Okay. So first we will find the linear approximation. So the linear approximation out of x at x equals 1 is given by the equation L of x is equal f of 1 plus f prime of 1 times x minus 1. Well, f of 1 is equal to root of 1 plus 3, that equal to f prime of 1. So then f prime of x is equal 1 over 2 root of x plus 3. That meant f prime of 1 equal to 1/4. So the linear approximation out of x is equal to 2 plus 1/4 times x minus 1. Now we want to estimate square root of 3.1. Okay, and we want to estimate square root of 3.1. So we know that f of x is equal to x plus 3. So if we want to estimate square root of 3.1, well then 3.1 equal to x plus 3. This man is telling us x here equal to 0.1. And so we can calculate the linear approximation of 0.1. Yeah. So this man that's equal to 2 plus 1/4. 0.1 minus 1. This equal to 1.775. So this telling us that, okay, then square root of 3.1 is approximate 1.775. Find the linear approximation of f of x equal 1 plus x to the n at x equal to 0, and use this approximation to estimate 0.01 to the third. Again, L of x at x equals 0 is L of x approximate to be f of 0 plus f prime of 0 times x minus 0. F of 0 equal 1. F prime of x is equal to n times 1 plus x to the n minus 1. F prime of 0 equal n times 1 plus 0 to the n minus 1. This equal n. So then we have L of x is equal to 1 plus n times x. Now if we want to estimate 1.001 to the third, we know that f of x is equal to 1 plus x to the n. and we want to estimate 1.001 to the third, which means x equal to 0.01 and n equal 3. So the linear approximation is equal to 1 plus 3 times 0.01, that is 1 plus 0.03, that is 1.03. So we can use this to estimate a lot of different things. Differential. Let y equal f of x to be a differential people function. The differential x is an independent variable. The differential dy is given by dy dx equal to f prime of x, right? This means dy equal f prime of x times dx. So how do we find the differential of this function y equal x times cosine of x? Well, then dy dx is equal cosine of x plus x times sine of x. Derivative of cosine equal negative sine. Okay. So then dy is equal to cosine of x minus x times sine of x dx. And why do we want to talk about this? Let's take a look at the geometric meaning of the differential. Let x equal to a. And we will let the change in x equal to dx. So let's say we are given a curve f of x, this blue curve here. Okay, we're given a curve f of x. And its tangent line, the red one here, okay, at this point f of a f of a. So when we do the linear approximation, so dx, the difference at the point from a to the next point, equal to delta x. Then the value of the function at a dx equal to a dx times a dx f of a dx, right? So the change in y is this distance here. The change in y, we're talking about this distance, this distance here. Okay. If delta y is then equal to f of a dx minus f of a, and whatever f of a is, this is this distance dy. Okay. Then the corresponding change in the tangent line, delta L, is equal to L times a plus dx minus L of a. So this here, the smaller distance, is your delta L. Okay. So then here you can see that if you take a look at the L of a plus dx, then we have f of a plus f prime of a times a plus dx minus a. There's just a substitution. Okay, we know that L of a equal to f of a. So then the delta L is now equal to the given equation, whereas the delta L is just f prime of a dx. Okay. So here what it's really saying is that geometrically the different dy is the change in delta L. It's a linear approximation of f when x equal a changed by an amount dx equal to delta x when dx is sufficiently small. Let y equal to x squared plus 2x. Compute delta y and dx and dy at x equals 3 given dx equals 0.1. Okay. Let's first compute the delta y. So delta y is equal to f of 1 plus 0.1 minus f of 1. Okay. So that equal to excuse me. Well, f delta y is equal to f of x plus dx minus f of x, and x here equal 3. So f of 3.1 minus f of 3, that equal to 0.81. Well, dy is equal to f prime of x times dx, and that is 2x plus 2 dx. So then dy in this case equal to 2 times x, well 2 times 3 plus 2 times dx, that's 0.1. So that is 8 times 0.1 equal to 0.8. So note that the value is very similar, right? Calculate the amount of error. Okay. So any type of measure is prone to a certain amount of error. In many applications, certain quantity are calculated based on the measure. For example, the volume of the sphere is calculated by the measure of the radius. The error in measure of the radius leads to an error in computation of the volume or the surface area. Let's use differentiation to estimate that error. So the error is the difference between dy and delta y. So how big is that error? Okay. So given f of x equal to x squared plus 2x, for x not equal to 3, find the change in delta y. We just did this earlier in the previous problem. Delta y equals 0.81. Part B, dy is equal to 0.8. The approximation error is the absolute value of delta y minus dy. That is 0.01 in this case. Okay. And take a look at this next problem. The radius of a circle measured with an error at most 2%. What is the maximum corresponding percentage error in computing the circle circumference? So let's start with the error at most 2%. So it means dr is at most 2%. So between negative 0.02 and 0.02. Okay. So let's take a look at what is the circumference. So circumference of the circle C in terms of r is equal to 2 pi r. So then dc dr is equal to 2 pi. So dc equal to 2 pi dr. So the error in the circumference, we will go ahead and manipulate in this formulas. So start with negative 0.02 less than equal dr less than equal 0.02. 2 pi dr is less than equal 2 pi times 0.02 less than equal negative 0.02 times 2 pi. So then the maximum error of the circumference DC is within this range. And what is it? That is 0.12 sit and negative 0.12 sit. So the maximum percentage error is about 12.6%. Yeah. So if you calculate if the error of the radius is 2%, then this error in the circumference is up to 12%.